Hey everyone, hope you're having a good Monday. We are back with another Mathman Mondays, and today we are going to be talking about basic integration. And the great thing about basic integration is we have talked about basic derivatives a couple weeks, or maybe it's a couple months ago now, and basically we're going to have an opposite operation. So since we talked about derivatives, now we have to talk about integrations. We have to have an opposite operation. Um, it is similar in a lot of ways to finding the inverse of a function. So when you think about integration, with it being our opposite operation, it works very similarly to how we would do a function. So if you remember when we took the derivative, so just as a reminder, it's been a little bit, let's talk about a derivative for a second and just talk about just a super basic derivative, just so we can kind of see the idea. With a derivative, we would say f of x equals 2x to the third. And if we wanted to find the derivative of that, what ends up happening is this value comes forward and then we subtract 1 from the power. So we end up with f prime of x is equal to 6x squared. So when I mentioned that we have an integral, it's the opposite operation. If you have an integral, kind of a odd word to say, then the idea is if we integrate 6x squared dx, we should get 2x cubed back. Now, the integral involves a few things. You have this, and tonight we're just talking about indefinite integrals. We're not going to go into definite. We have this kind of like S curve thing going on, and we have our function. So we have our f of x and we have our dx. So important to note here that those things exist. So this is like our f of x, as I kind of messed that up, and our dx. And what this means is we need to have a function and the derivative of that function in order to work. This isn't as important with the basic derivative part, but when you have to do substitution later on down the road, you need these things to exist. So let's talk about what happens when you integrate. When you integrate, unlike when you're a derivative and you subtract, since it's the opposite operation, you add. And then whatever was in that power, that 2 plus 1, goes to the denominator. All right, so you add, and then you take it to the denominator. So add 1, whatever that power is now your denominator. So when that happens, a couple things happen here. You end up getting 6x squared, 2 plus 1 is 3, so it's not squared anymore. 6x cubed over 3. Hey, and the dx goes away. So as soon as you integrate, the derivative goes away because they're opposite operations. Then there's actually more to that gets really mathy. We're not going to get into that. Just know that dx goes away for now, and don't get too hung up on that. What is 6 divided by 3? Well, I am really hoping that's 2. So we get 2x cubed. So we're working with an opposite operation. The cool thing about integrals and what they do compared to derivatives, we find a tangent line. But when we talk about integrals, we are finding, what's really embarrassing? Not being able to spell. Wow. I apologize. F's in the chat. That was bad. If you're watching this on YouTube, I am extremely sorry for the spelling error that you had to see. It's a good thing I'm a mathematician, not an English teacher. All right. So going back to what I was saying, is the cool thing is derivatives we're finding a tangent line, but with the integral we're finding the area under the curve. And we can talk about that in a few different ways. We really like to look at it as a positive area when we're working with functions. So just to give like this brief idea, if you had this function and we have 2x cubed, so just bear with me for a second. Now, when we talk about the indefinite integral, we haven't put a bound on it. What the definite integral does is it gives you a lower bound and an upper bound, and those bounds limit you where you are. So let's say we're from 0 and we'll go to 1, 2 or something like that. You could find this shaded area in here and find the area under this curve. That's a little bit later on down the road, but gives you a little bit of an example to kind of think about going forward. So the thing that we have to remember with integrals is, just like with derivatives, there is a lot of different properties. So what I just showed you is a very common power rule, and that's nothing crazy. And I actually left something off there that was really important. Whenever you have the integral and you're doing an indefinite integral, we're going to have to put plus c at the end. And we'll do some examples in a second. But for a moment, I'm going to go through and kind of walk you through some of the different variables that could happen. So, or some of the different rules that could happen. Sorry, not variables. I'm going to use variables. So you have a constant rule. The constant rule says you have an integral and you put any constant you want. So let's put 5. And then we put dx. All right, well, there is no variable there. And another way to look at this, because we're trying to think about, is there actually is one there. So let's look at it like this. We have the integral of 5 x to the 0 power dx. That way you have an idea of how this came about. Well, anything to the 0 power is 1. 5 times 1 is 5. So this works okay. We're going to do plus 1 over 1. And then over here, we're going to get equals. And we're going to get our, now what is going to be 5x. Anything divided by 1 is itself. So we end up with 5x. And every time you do an indefinite integral, and I didn't write this in the last example, you put a plus c. Because the derivative of a constant is 0. So you have to remember, we're doing what is known as the antiderivative. It is probably good to note that somewhere. So if you're taking any notes over this, you want to remember that integral, spelt right, integral, is the same thing as antiderivative. There wasn't a lot of room to write that there. Is the same thing as antiderivative. There's no reason to think about it any other way. So that kind of gives you an example there. And it's actually easier for my students when I'm teaching to call it the antiderivative. Anytime I use the word integral, they'll go, what's that? They're cool with it for like the first section or two, and after that they'll be like, what's that? Or if I take a week off from talking about them, they're like, hey, what's integral? It's the antiderivative. Oh, yeah, that's right. So just food for thought. It might be better to use antiderivative as a vocabulary word for that. As we move forward, now we'll talk about the variable rule. And with the variable rule, this is very similar to what we just did. We just saw it in this one because I added that in. But also we saw it in the previous example when I said, hey, let's look at a basic one. So in this case, if you just had the integral x dx, right, you have to remember the x power here is 1. So we add 1 to it, and we put it over 1 plus 1. So we end up with x squared over 2 plus c. Super simple. No reason to really overthink that. Then you have what is known as a reciprocal rule. And it might be worth noting that natural log is really important here. So the integral of 1 over x, and you can see this written two ways. You can see it written as 1 over x dx. The other way it is written is, depending on who is writing the notation for you, is dx over x. There is really no difference, but depending on the textbook that you're using, that your instructor is using, you could see one of these two options, and they're exactly the same. So I want to make sure to notate both of them. All right, there's actually a couple ways to look at this, but this actually works out to be a rule for us. So what you're thinking, or what generally happens here, is you end up moving this up, things happen, it's not good. You need to know that whenever you see this in the integral up front, that's this natural log of x. It's actually natural log of absolute value of x plus c. And when you ask me why is it the absolute value of x, all right, I want you to go put in, let's say x is 5. Go do natural log of 5, and then go do natural log of negative 5, and let me know what happens. One of them will work and one of them won't. So we end up with natural log of x plus c. Sorry that it was in a different color. Let me go back if you are color coordinating and make sure that that is the same. So we have natural log of x plus c. Okay, so those are our first three rules. We're going to go over a couple more here in a second, but I want to give you a second just to have those written down. So there's a lot of rules here, and these three are very common. There are three common trig rules that we're going to talk about too. I'm also going to include the exponential rules that are actually a little bit more difficult and would not be covered in here, because I think it's important to kind of see what's going to happen later on, but also to give you time or to really think about it. So, because sometimes they'll put those type of problems in these beginner sections with no explanation just to kind of see what you do. So, those are our first three. And I'm including an example with each one because I think it's important to just have a nice little example. Rather than writing out all the rules and then writing out the examples, here we'll cover it in a little bit of different format than I typically would in my classroom. So, this moves us on to the exponential rules. And for the exponential rules, we're actually dealing with three different problems. We're going to have one, the absolute value of e to the x dx. Two, the absolute value of a to the x dx. And three, the absolute value of natural log of x dx. And these are their most basic rules. It doesn't change too much either way. I like to think about it as u substitution, which isn't happening yet. So, for instance, I would think about it as when you do the rule, it'd be u prime of e to the u plus c. Or here we'd have u prime a to the x, oopsies, a to the u over u prime natural log of a plus c. I think that one's right. And you get the idea. We're not going to use these u's right now, but the idea, and I'll show it with this first one, and you can go look at these later, is that if we had a different function, so let me write this out in purple. If we had the integral of e to the 2x dx, we would say, hey, what's the derivative of 2x? So you'd say, hey, u is equal to 2x du, or what I like to write it as u prime because I'm really lazy. U prime is 2, and my answer to this would end up being 2 e to the 2x plus c. So that's the rule using u substitution, which you learn later on. Right now, when they bring this up, they are only concerned with you knowing the following. So sorry for the little tangent there and getting off track, but I want you to know that this isn't the exact rule. Like, there's another part to it, is you're going to be using just e to the x plus c. And the reason you get e to the x plus c is if we go back and we think about the u is x and the u prime, so the derivative of x is just 1. So if you write a 1 out front, what happens? Nothing. All right, I'm just giving you kind of food for thought that you're going to see this at first, and then they're going to, all of a sudden they're going to be like, oh yeah, by the way, you can do u prime. So as to not be caught off guard, I'm including that now for at least this first example. The second example here is you get a to the x over natural log of a plus c. And then for natural log of x, you get x natural log of x minus x plus c. It gives you some kind of things to think about. Okay. These are the very beginner rules. You'll see them again with u's and u primes in the relatively near future if you're doing basic integration. So hopefully that was helpful and not too confusing. If it was, I'm sorry. And the next part might be slightly better. So to cap off our basic integration, well, not to cap off, actually, we have one more set of rules, and then I want to talk about just a couple other little like fundamental things. So to cap off the actual rules part before getting to the fundamentals, we have the trig rules. There are basically three that you see a lot of, and you would see the integral of cosine x dx. You would see the integral of sine x dx, and you would see the integral of secant squared x dx. Now, the reason these are important is you have to think about how the derivative works. So if you take the derivative of sine, you get cosine. Therefore, the integral of cosine is sine x plus c, because we have to think about this is the opposite operation of a derivative. So if I think about how do I get sine x, well, I'd have to use a negative cosine x, because the derivative of cosine of x is negative sine. So a negative would give you a positive. And then I'll leave this one for you to kind of think about. Tangent x plus c. Go back and look at derivative rules and just see how that goes. Those are pretty easy. It has you having to remember trig. Okay, so I've given you the basics of everything that's happening. I want to talk about some other stuff real quick, in the fact of, let's say you have a constant, so multiplication if you have multiplication of a constant, so you have the integral of some constant times f of x dx. And we can think about this another way. So if we have the integral of 3 times x plus 2 dx, you have options. You could distribute the 3 and then take the integral. But what the rule says is you can actually just take the constant out front. So you can go from here to here and get the integral, or c integral f of x dx, which means if I rewrite this integral, I could just say 3, the integral of x plus 2 dx. I can just pull that constant out front and not deal with it ahead of time. What up, Depp? Thanks for tuning in, my dude. So gives you a way to pull that out front. In this case, it'd probably be easier to distribute, but you do have cases where it's easier to remove that constant and bring it out front. So that's one. You also have what is the negative exponent rule. I didn't cover it earlier because people get this confused when they deal with the trig function with natural log, so the reciprocal rule. And when they see this, so for instance, the integral of 1 over x dx is equal to natural log of x plus c. All right, don't mess with it. If you see that, leave it alone. But you do have another one where you deal with negative exponents. And this is important because if you have anything else, like 1 over x squared dx, you want to be able to deal with that. So if you're dealing with a negative exponent, you just bring up the negative and you rewrite it and you say, hey, the integral of x the negative 2 dx, and then you integrate as normal. All right. If you have just x, it's natural log of x. But if you have anything else in that power, then you come back and you say, okay, well, plus 1 over negative 2 plus 1. Well, that gives me x to the negative 1 over negative 1 plus c. And if I go over here a little bit, gosh darn it, my color coordinating peeps, I'm sorry. It's supposed to be in brown. X to the negative 1 over negative 1 plus c. I move this back to the denominator. I end up with 1 over, or you can write it as negative 1 over x plus c. So if you have that negative exponent, deal with it. Nothing too crazy. Just make sure you're looking at it correctly. Now, what I'm going to leave you with is this. If you have, and I'm going to call this sum and difference. So sum slash difference. If you have the integral of f of x plus g of x dx, and you could write it like this, if you just had two functions added together, or just two different items added together, you can actually go through and separate this out, and that would be beneficial to you. You could just do the integral of f of x dx plus the integral of g of x dx. And maybe it's because you want to use different rules, but you have that opportunity to where you can separate them because they are sum and difference. I'm not going to get too much into the substitution rule or the integration by parts because I consider that not to be basic integration anymore. Everything I covered tonight, I think, is part of a basic integration that you would see in the introductory parts of integrals. So I didn't talk too much about how area under the curve is calculated because I think that's something you would see later on. If that's something you're interested in and want to know more about, I will happily do another MathMan Monday just on that topic alone because you could take the time to do that. And what you're going to use is something called Riemann sums, and they're basically using the areas of rectangles to find area under the curve. Later on, we found out integrals, so on and so forth. Not going to get too far into that. I do hope this was helpful to you. I tried to cover basic rules and give examples that weren't too terribly crazy, so it'd make it easier to follow. If you're watching this on YouTube, always feel free to leave me a comment. I apologize that the last video I made, for some reason, it uploaded to YouTube as private and didn't get posted. It should be up there now. It's about linear regression. I made sure that was up today and working. For some reason, it just didn't work out right. But that is the end of my lesson on basic integration. I hope you enjoyed it. I'll be back hopefully next Monday with another topic. What it will be, I don't know. Check it out on Twitter. If you need a link to that, it is below. If you need a link to the YouTube, it is below. There is a playlist. You can just search Blazes the MathMan Mondays and find it. And they all go there. This video should be up hopefully tomorrow night or Wednesday. And I hope you have a great rest of the week. I will be hopping over to Smite to do some ranked duels. And I'll catch you guys later.